hear me and can see my slide. Welcome to the lecture of this week, in my case. But before we start with the lecture, I would like to say something why or that we run some of the lectures via online. We have had this semester a little bit of problem, and I have heard some of you have a little bit complain that you have so much online. I can understand that very well. It is not the optimum, but the problem is that we was informed by our university that from until the deadline of the applications in the 1st of November, that everything in the next semester can be in presence. And that was clear until the 1st of November, until the deadline of the applications. But shortly after this, after the deadline, we got the information that from January 2022, everything has to be via online again, because we have had in November extremely increasing cases, increasing numbers of COVID-19. And so we have sitting together with all my colleagues, and we have handled the question, should we open again the application round also for students who cannot come to Osnabrück? And we have decided to do that, so that we have opened the application round new also for students who cannot come to Osnabrück. And we got some applications, especially from Malaysia, from students where we have known that they cannot come in presence. And from January, we have had to do then every lecture online, but in February came the announcement of the university that we can do again everything in presence from March. And now we have had a big problem. We have students who are in presence, and we have students who are not in Osnabrück, but we have to serve both kind of students. And so all colleagues have found a way to make a mix. Partly, in my case, for example, the lecture is via Zoom, and the laboratory work, what we do in the end of the semester, that is also in my case in presence. And the students who are not cannot be in the lab, these students we connect then also in the lab via Zoom to the students who are in presence in the lab, so that we have a mix from presence and Zoom. I know that is not the optimum. It is not so good. And I hope that we get in the next round, when we have the quality engineering course the next time, that we get, before we start with the course and before we have the application, that we get a clear announcement of the university. Can it be in presence? Can it be or has it to be online? But this semester we have to live with this situation, that we have to serve both kinds of students. And I can apologize me for this case, but I hope you understand why we have to do this in this kind. An additional problem is that in some of the of the lecture halls, we have a bad connection to the internet. And so that not in all lecture halls we can make it so that we make the lecture in presence and let run a camera for the Zoom students, for the online students parallel. That is not working everywhere. I hope you have understanding for this situation, and I hope that is only in this semester so. Yeah, have you questions for this?
For the moment, we continue having the course online?
Yes.
Okay. And if we have a bad connection, I didn't understand.
No, I'm not in the lecture hall. We have, for example, I know Mr. Schrader. He is in another lecture hall, and he make it in presence, and he let run for the online students a camera parallel. But in this room it works, but it works not in every room. And therefore, for example, in my case, we make the lecture via Zoom, but in the end of the semester, the laboratory work we make in presence.
Yes, okay.
Because that is in the laboratory, and there we have a better internet connection. We can switch the students who cannot be present in the laboratory work. We can connect them there.
Okay, thank you.
Okay, I hope you understand this situation. It's not the optimum. I know that, especially for the students who are in presence, and you accept also a lecture in presence, but then have we a problem with the students who have applied, where was from the beginning absolutely clear that they cannot come, that they cannot make it in presence. I hope we get better times when Corona is gone, and it is then from the beginning clear that we can do everything in presence, and then we know we take only students who are in present here, and we can do it then also in presence. But I would like to say you that that we know that is not the best situation, but I hope that you understand why we have to do that so. Okay. When you have no questions, you can every time ask. I have switched on all the microphones. We are only 16 students, or 15, one is me, 15 students, so that you can every time ask when you have questions or remarks or what else. I think that was the last slide in the last lecture. We have had in the last lecture the description of the random error. And you have seen that the scientific method of the description of the random error is the standard deviation. The standard deviation, and you can do a lot with the standard deviation. You can also calculate the average error of the mean. You see here is the standard deviation in and the number of measurement values. We have spoken about this, but the standard deviation is every time connected to a possibility. And you can say the single standard deviation in this range are the measurement values with 68.3%. And in the double standard deviation, you have 95.5%. But that is every time so that the error is connected to a possibility. And that is the scientific method. But for the industry, we have a second way, and this second way is not a clear mathematical way. It is not absolutely mathematical correct. And this is the accuracy class. The accuracy class is a second way to describe the random error, and it is very often used in the industry. It is much more easier as the scientific way with the standard deviation. It is much more easier, but it is mathematically not completely correct. We say the accuracy class is a maximum expecting error in percent of the measuring range. And typical accuracy classes you have here, especially in electrical engineering, the voltage and current measurement devices working with accuracy class 1 or 1.5. That is very typical, but you can have everything here, but that are typical classes. And I would like to make an example. You have a voltage meter. The accuracy class is 1, and the range is 0 to 100 volt. And that means by displayed 100 volt, the maximum error is 100 volt plus minus 1%. That means plus minus 1 volt. And the producer of this device, the manufacturer, say you will never measure a bigger error. And therefore, he determines this percent so that he is measuring very often, and has looked for the biggest error what he has ever measured. And let me say the biggest error was 1.7 volt. And then he put a little bit on top. And that is not a scientific way. He put a little bit on top because he say you will never, the applicant will never measure more than my given accuracy class. And when he has a high security feeling, then he say, I put a little bit more on top. Another manufacturer say maybe I say 1.5% with the same measured error of 0.7. And this is not a scientific way, but it is often used in the industry. And when you have balances and when you have electrical measurement devices, you can see on the display the accuracy class. But the problem is you measure, for example, and come back to this example, 100 volt plus minus 1 volt. By display 10 volt, the maximum error is also 10 volt plus minus 1 volt. That means that the relatively error is increasing when you measure in the lower part of the range. And from this is coming the requirement that we say, please use the range so much as possible. For practical application, we say, if possible, the last third of the range is to use. There is no reason for the last third. Better would be when we would say the requirement is use the range so much as possible. That is more exactly that what we want. But for the practical applicants, we say you should measure in the last third of the range, because the relatively error is there lower. And I have written here, the accuracy class is a compromise of an exactly error analysis with the standard deviation and the possibility, and an easy usability. Many manufacturers and users of measurement devices in the industry prefer it more easy, not so much calculations and so on. And so the accuracy class is very easy to understand, but especially at the determination of the accuracy class, that is not a scientific method. You measure the biggest error what you have measured and put a little bit on top that you can say the user will never measure a bigger error as I have promised him. Therefore, you should know that this method exists, but when you write a scientific paper or your final year project or what else, then should you use the standard deviation, because that is a scientific method to express the random error. Have you questions to the description of the random error? No. Then we come to the systematic error. You remember, this is a second big group of errors, the systematic errors. And, and the systematic errors, sorry, the systematic errors are known and predictable for amplitude, sign, and time of appearance. That means we know exactly this error. And when we know an error, then can we also correct this error, and we should also correct this error. And I have here a small table. When you have a linear function, you have every time a multiplicative constant and you have an additive constant. That are the expression in the mathematic. In the electronic, we have the same things, but we call it amplification, but that is the same as a multiplicative constant. And we speak from offset, that is the same like the additive constant. And in metrology, we say sensitivity for the amplification, and we speak from 0 point from the offset, but in many cases directly from the 0 point error, because when a measurement device shows something when it should be 0, then it is clear that it is an error. And now I have here a very, very important picture. This picture you must know absolutely, because that is a basic for everything what we do in the field of calibration, of computer-aided calculation of measurement results, and therefore to understand the whole system, to have the overview, you should understand very well this picture. We have a true value. What is going in our system? The true value X, that can be, for example, a temperature. You would like to measure the temperature, and you have here the temperature, let me say 20 centigrades. And now you have a transfer function. The transfer function, in the first step, we say it is a linear function. Later, we will make it also with a non-linear function. The linear function has mx plus n. You see, you have a multiplicative constant and you have an additive constant. Normally, the system should have the function y is x, but in practical applications, it isn't so. You have here the amplifier, and you have the analog digital converter. And what you get as the uncorrected value y is, in the most cases, a number from an ADC, a number from the analog digital converter. And for example, when you have a 12-bit ADC, these numbers are between 0 and 4096. These numbers you give into the computer. This is a computer. And your 20 centigrades, what you have put in, leads to a number between 0 and 4096. And at this point, the computer don't know what is that, this number, what he get. Is this a temperature? Is it a pressure? Is it a speed or something? He get only this unified number. And now the computer need a correction function. You can say correction function or calibration function, that is the same. The computer need a correction function where you calculate the y under the condition that this y is equal to this x. That means from the ADC number, you have to calculate again your 20 centigrades. And for this, you need, or the aim function is y is x, and you need to make the n what you have here on the left side, this n plus a correction for n, kn leads to 0. And km multiplied with m leads to 1. I have it written here. This y uncorrected, the ADC number, what the computer is reading in, is mx plus n. That is a linear function at this point, but the linear function has an m and an n, and is not only the x. And therefore, you have to calculate the n and to calculate the correction constant for n. And you see here n plus kn must be 0, therefore kn is minus n. And km multiplied with m has to be 1. And therefore, km is 1 divided by m. And what is standing in the end here is this x. That means y is x. Because over the whole system, you must have every time the aim function y is x. That is every time the aim. When you put 20 centigrades in, you have to display 20 centigrades. When it is a balance, you put 5 kilo on. You have here the same values from the ADC. That means the computer gets the same values from the ADC, but he has now to calculate 5 kilogram from these values between 0 and 4096. And when you have only a low resolution, let me say an 8-bit ADC, then have you numbers from 0 to 256. That is then a lower resolution, but the system is the same. The system is absolutely the same. Have you question to this point? Okay, Then the whole mathematic is extremely simple. That is everything what we need. And you see, it is extremely simple, but I give every time a little warning at this point. You must know what you do. You must have to understand the system of calibration. The mathematics is extremely simple, but you must have understand that what we do, the system of calibration. Yeah, you can calculate m with delta y divided by delta x. That means when we have this transfer function, then you calculate delta y uncorrected by delta x. And then can you calculate the km, and because km multiplied with m is 1, then km is 1 divided by m. N you can calculate with the same function, and when you have calculated the n, you can say n plus kn has to be 0, therefore kn is minus n. And here you have the correction function, or you can call it also the calibration function. That is the guideline on the computer to calculate the true value from your ADC number. And when we adapt the input voltage or the input characteristic to our ADC input, then we can do it so that, let me say here, that we can make it better in the lower range, then have you a bigger error in the bigger range, or you make it better here and then have you a bigger error here. But today we make it normally every time so that we look for the 0 point and the biggest point. And also when the curve would go so that we have a big error between these two, we make it so because we can correct step by step also a non-linearity. And let me, before we make this example, I would like to show you the practical background, and I switch my drawing on. I hope you can see my drawing platform. So let me say you have a sensor. You have a sensor and you would like to measure 0 to 100 centigrade. And this sensor gives a voltage. Let me say for 0, 3 microvolt, and for 100, let me say 35 microvolt. That's what the sensor gives you. And now we have to amplify this. We have to amplify this with an amplification. And you have then here the amplification. Yeah, let me make it so. The amplification, and the amplification has to be so that you come on an input range of an analog digital converter. This is the analog side, that is a digital side. And here you have, depending from the resolution, the output lines. Let me say it's 12-bit. It's difficult to write. 12-bit, then is the lowest 0 and the biggest is 4096. But you need here a defined input range. And in many cases, we go from 0 to 5 volt. That means this amplifier has to make it so that the 3 microvolt leads to 0 and the 35 microvolt leads to 5 volt. So you have to make the dimension of the resistances of the amplifier that you have for this range, this voltage. And that means in the end, 0 would be 0 volt, 100 centigrades would be 5 volt. And on the output side, 0 would be 0 volt, 0 bit. The bit number is 0, and 100 volt, 100 centigrades leads to the bit number 4096. And now you go to the, this is Y uncorrected. And now you go to the PC, and the PC need your calibration function so that you calculate from the PC here the Y, and Y should be exactly like this value X. Here you go into your PC. And how that works, that will I explain, so that you have a practical application. And when we are in the laboratory, we will run an experiment exactly on this basis, that you calibrate a length measurement from 0 to 50 centimeter with light, and we calibrate this device then in the laboratory. But at first, I will make an example. In this case, I have told you that everything is linear, but that must not be. When this sensor, for example, has a non-linearity, then we said this 0 point, that is from the sensor 3 microvolt. The highest point is 35 microvolt. We have here the output side, that is from the sensor. And that is output of the amplifier. This output of the amplifier, and we said this should be 5 volt. That is the output point here of the amplifier. But it can be linear, but it must not be linear. It can also be that we have this curve. But we look that the 0 point is clear, the lowest point and the highest point must be fit to the output voltage. When we have now here a huge error between, then we have to calibrate it step by step with linear functions. We approximate with linear functions and calibrate this function to the true curve. And how we do that, I will explain at an example. This is an example, and let me say we have a length measurement, but in this case it is a resistance. You have a glider or a slider here. This slider is going up and down, and you have here 0 centimeter, 10 centimeter. The resistance is a linear resistance with 10 kilo ohm. That means 1 kilo ohm per centimeter. And you get here the voltage out, what you have, what you give in your computer as a number in your computer. You run with 5 volt, and important is this resistance. Why is this resistance here? I will explain it in my drawing field. So we relate it. Yes. When you have a linear resistance and you go here to the output side, this is the ground, and you have here the 5 volt. Then have you here an output signal which is linear. Linear, that is minus, that is the ground, and here you have the plus 5 volt. And that would be a linear function when you have here the centimeter, and you have here the voltage, the output voltage, it would be linear. But the problem is, when you have this sensor, for example, on a garden gate or on a garage or everywhere where you would like to see the position, then have you a long wire to your electronic. And this wire get disturbances from outside, so that you have a noise, you have random errors, and you know random errors we cannot correct because we don't know when these random errors come and what the amplitude of this induction, of this influence from outside is. And what you can do is that you let flow a current, a constant current over a resistance on this side, so that you have a constant current over, a continuously current over this resistance. And therefore, you have more power on this line, and the disturbances have not so big influence because they must be from the energy higher as the energy of this wire, so that you increase the difference between your signal and your noise from outside. That means you get a lower random error, when you let flow here a little bit of energy. But the problem is, now you have an non-linear output, because that is a loaded voltage divider. You have a charge on the voltage divider, and that makes the output signal non-linear. When you have the resistance, you will get this non-linearity. And when you make this load bigger, that means you take a smaller resistance, not 5 kilo ohm, when you make it to 2 kilo ohm, for example, then have you again a lower influence from the signals from outside, because you have more energy on the line. But your non-linearity will again bigger. And this non-linearity is a systematic error. In this case, we change the random error, what we not can correct. We change this random error to a systematic error. But the systematic error we can correct. And we would take a line here, then we approximate with the second line, third line, and so on. And we correct step by step for every interval, we correct this nonlinearity. And that I would like to show you in the example. You see here again, this picture, what we have had already. You have the measurement system. This is a measurement system. And you go with this number in your PC, and on your PC, you have to have the correction function. That is the guideline to calculate the true value. Because when you put 2 centimeter in, you expect that your computer calculated 2 centimeter. Also, when you have for y uncorrected, in this case, a voltage value. So, and in my present lectures, I let calculate it from the students, because especially students who come from electrical engineering, they have to calculate it, the resistance. But I show you what the result is. And you see here at 0, of course, is the voltage 0. And at 10 centimeters, the voltage is 5 volt, because that is the upper, the top of the resistance. And between, you can calculate the voltage with the load of this 5 kilo ohm, with the load of this 5 kilo ohm. And you see here, you have an non-linearity. And in this case, we can say we approximate with a line approximation between 2 points, 0 to 0.76. Please remark this, please note, this is a German dot. Yes, the German dot is a comma, 0.76 volt at 2 centimeter. And when you go here to 2 centimeter, you have this 0.76. And you can calculate a linear function for this interval. And you can look for the next interval from 0.76 to 1.35. And that is the interval from 2 to 4. That means from here to here. You approximate again with a linear function and correct this linear function so that you can correct in the end also the nonlinear function when you approximate step by step everything with linear functions. And that is a calculation for this. You have here the points, that is the uncorrected value, and that is the true value. And the true value is 0, 2, 4, 6, 8, 10 centimeter. And here you have the voltage, what the computer has to read in for these points. And now you calculate at first the M, the amplification, the sensitivity, the multiplicative constant, everything is the same between these 2 points. And that can you look here, delta y divided by delta x. That is this. Delta y would be 0.76 divided by delta x divided by 2 in this case would be this. And then you have to calculate the n, and the n is y uncorrected minus m multiplied with x. And in this case, is it 0? Because we have here 0, but in the other lines have also an n. And you see also the sign plus or minus can change. That can be that it is changing from one line to another line. This linear function is valid in the range between these 2 points. And the same function, but with this n and this m, is valid between these 2 points, and so on. And now you can calculate the calibration constants. The calibration constants, Km and Kn. We said Km is 1 divided by m. 1 divided by m, 1 divided by this is this one. 1 divided by m here is this one. And we said n is minus x. Kn is minus n, sorry. Kn is minus n. Of course, when n is 0, then is also Kn 0. But here you see n is plus 0.17, Kn is minus 0.17. When n is minus 0.01, then Kn is plus 0.01. It's only changing the sign. And with these values, these are your calibration values for your device. For every line, you can have this formula. You read in your computer y uncorrected. You have to look y uncorrected in which line you are, and then have you to use this correction function from the line where you are. And this can you do in a short program. This is a program written in BASIC or Turbo Basic. It's a very, very easy programming language. This is only the line number and you can read it. Y uncorrected is read in the uncorrected value. That means, I go back, that means the uncorrected value will be read into your computer. And then the computer asks, if y uncorrected is less than 0.76, then use the first correction function, and in the end, go to line 110, print the value, for example. That means if y uncorrected is less than 0.76, then go in the first line. If y uncorrected is less than 0.76, then use this correction function, this calibration function, this function with these values. And when you are here, when it is bigger, when it is not 0.76, when it is lower than 2.03, then use this correction function. And now we make an example. Let me say your sensor, I go back, your sensor can stop on every point. And let me say the sensor is standing on 5 centimeter. On 5 centimeter, you get a voltage for 5 centimeter. What is the voltage for 5 centimeter? 4 you have this, 6 you have this, and you can calculate the voltage for 5 centimeter. Please do it. Please calculate the voltage for 5 centimeter. I do it also. And when you have the value, you can say it. That would be the middle between 0.35 and 2.03. 2.03. So I get a voltage for 5 centimeter from 1.69. 1.69, when your sensor is on 5 centimeter, you get 1.69. 1.69 volt. And in your program, you say, if Y uncorrected is less than 0.76. That's not true. Therefore, he asks the next line. If Y uncorrected is 0.35, that's also not true because our value is 1.69. The next line, if Y uncorrected is less than 2.03, that is true. That is true. 1.69 is our value. Then calculate this function. 1.69 plus 0.01 multiplied with 2.94. You can calculate this, and the result must be 15 centimeter. You can check it. The result must be 15 centimeter. That means this program is the guideline for the computer how to calculate from these uncorrected values the true value in centimeter. And that for every point on the sensor, because you get for every point an voltage, and you go in the program and look where you are, in which line you are, and then you calculate with the right calibration constant. Have you understand that at first? Please ask when there are questions. Okay, then I will show you why we have here a change. You see, we ask every time less than 0.35, less than 2.03, less than 3.03. But in the last line, we ask bigger than 3.03. Why? We do not ask less than 5. Because we have here every time asked less than 2.03, take this line. Less than 2.03, 3.03, take this line. It would be possible to say less than 5, then take this line. But when you have random errors and you have possibly, you measure 5.1, what shall the computer do in this case? And therefore, for the last line, we ask not less than 5, we ask bigger than 3.03. Take this line. And this include also values which are possibly bigger than 5 volt from random errors. Then you would calculate also a value bigger than 10 centimeter, and you know you are out of the range. That means all the error classes or standard deviations are not anymore valid because you are out of the range, but the computer know what he has to do. Therefore, the last line asks then, is the value bigger than the y uncorrected before the last y uncorrected? This is so far clear. Of course, this software you can write in every language. You can write it in C++, you can write it in Fortran, Pascal, what else? You can write it in Python. In every language can you write this principle. Important is that you have understand the principle, that you ask for the interval, that you ask in which line is the value, and then take the right calibration function for this interval where you are. Yes, yeah, let me say so. We have calculated these values. That is a systematic error because 0.76 is not 2. And we have to calculate from the 0.76 the 2 centimeter. But what is when you measure many times and you have additional and random error? And now I mix you the systematic error and the random error. You measure the first time 0.76. The next time you measure, you have 0.75. The next time you have 0.77, and so on. You have a scattering around a value because you have also random errors in. And then have we to divide the errors in the random part and the systematic part. And that can we do because we can calculate the mean. You have here the y uncorrected. You have the single values you have measured, let me say, at 1 point. I have here a length measurement. You have 10 centimeter, and you see you have measured many times at 10 centimeter, and you have a scattering value. That means you have random errors in. Now you can calculate the mean, and the difference between the mean and the true value. That is a part of the systematic error, because the mean, it's repeating every time. The mean is repeating every time. He comes in the mean every time again. The single value can be different from the mean. And when you calculate a single value which is exactly on the mean, you calculate the true value. But when you have the same calibration function, and that's the case, then when you calculate a single value which is bigger than the mean, you calculate also a true value which is bigger than the value which is bigger than the true value. And so you see, you have the random error also in the corrected values, the mean over the corrected values. That should be the true value. But the single values can scattering around the mean of the corrected values. And that means the random error you cannot correct. You can correct the mean to the mean, but not the single values. Therefore, important is that you remember that the keyword in this point is the calculation of the mean. The mean, the difference between the mean and the true value is the systematic errors. Is a systematic error. Therefore, here we have the y uncorrected, and the y uncorrected is the mean. The single value can be a little bit different, but with what you can calculate your calibration function, that is the mean. So that is a practical determination of the random and the systematic part of the error. And now I show you this experiment, what we later also will do in the laboratory, so that we can practically calibrate and devise, that we learn how to calibrate and devise. And this kind, let me go back, this kind of software have you today in every device. Also, when you have a washing machine and you display a temperature, you have exactly this behind. When you have a coffee cooker and there is a temperature displaying of the water, you have exactly this behind. Therefore, this calibration of measurement devices is a extremely fundamental thing what you have today in the daily life everywhere. Have your devices where you have such a function in. You can write it in every language, I told you that already, and you can also implement it on a small microcontroller, you can implement it on PCs, you can implement it on a single chip controller, everywhere where you can program in any kind of language. So come we to this example. What we would like to measure is the distance between our sensor and a reflector. The reflector is only a paper, a white paper, and we have here a light source. This light source irradiates against this paper, and with a photoresistance, we look for a point on this reflector and measure the brightness. Here you have the resistance and we measure the brightness. You have the power supply. I think we have 12 volt in this case. And you read in your computer the voltage over the photoresistance. And we have in the computer a 10-bit ADC, so that your numbers are going from 0 to 1024. That is the 12-bit, the range of the 12-bit ADC. And now we look at first what's going on when we move the sensor back and come to closer to the reflector. And then I go again in my drawing. We have here the reflector. It's difficult, right? And you have here your light source, and your light source makes irradiate here an area. And when you go, you have, or let me say, you have here your photoresistor, and you look for a point here in this field. When you now go back with your sensor, and you now move it away from the reflector, then have you a bigger area, and you look on this point. And that means when you have here the distance in centimeter, and when you have here the brightness, then you can say you start and it must be lower when you go away. The question is, in which kind will it be go lower? And you see, you have the same amount of light on a bigger area. Therefore, the intensity of the light on one point must decrease with the function of powered by 2. It must be a nonlinear function with a decrease of powered by 2, because you have the same light on the bigger area. But when you go more far away, you get also light from your table maybe back, so that you have maybe here an additional nonlinearity. Or when you are really far away, a lot is going into the nirvana anywhere, and nothing's come back. Then have you maybe again an additional nonlinearity. And these additional nonlinearities are also systematic errors, because they occur every time at the same distance, with the same amplitude, with the same sign, plus or minus. And so also these additional nonlinearities are systematic errors, and you can correct also these errors. That makes, or that is so that it makes not a difference what is doing the light on the reflector, so long as it is systematic, so long it is occur every time in the same way, you can also correct this. But another point is, we measured, let me say, we have start with 10 centimeter. We have start with 10 centimeter. And when you come closer and closer and closer, normally it should increase. The brightness should increase. But anyway, you are completely on the reflector, and the reflector covered your light bulb, the reflector covered your sensor, and it is absolutely dark, so dark as when you were in an infinite distance. That means here anywhere it is going again down. And that means here your system don't working anymore. And that have you in many cases, in many electronic devices, that you have not only an upper end of the range, you have also an lower end of the range, because when the signal is too small, in this case, your system is completely failed. But it can also be that you come into incredible noise, for example, with electronic devices. Therefore, many electronic devices gives also an lower point of the range, which is not of the working range, which is not zero. And we have also defined in this case the lower point to 10 centimeter and the higher point to 50 centimeter, because when you are too far, you get a lot of influences from outside, and the random error will be more and more, has more and more influence, and so it's not working properly anymore. Therefore, we have defined our range from 10 to 50 centimeter, where we can measure the distance. So I go back to, yeah, that is the equipment. We have here a lineal, that is a standard in centimeter, and with this lineal we calibrate the device. But the aim, of course, is in the end you should can take this lineal away and can measure only with this sensor the distance between the sensor and the reflector, so that you can data mine the position, you can data mine the distance, and you can take the calibration standard away. Yeah, what we do is this points, all these points from 1 to 10. And in this task, you have everything what we have done in the lecture until now. You have the calculation of the systematic error, the correction of the systematic error. You have to write the correction software. You can test the software also in values between the calibration points. And in the end, you should calculate the empirical standard deviation. That means the scientific method of the expression of the random error, and you should calculate the error class. That means that you calculate the expression of the random error with a non-scientific method, with a often practical used method. And here we have the measurement results. And the measurement results, you see, we have measured at 10, 20, 30, 40, 50 centimeter. And we have measured many times, 10 times at every point. You see you have scattering values. That means there is a random error and a systematic error in. And now we have to calculate all that what we would like to know. I think I calculated for you, but I have also uploaded an additional task. from the Mid-Sweden University. I have given some lectures at the Mid-Sweden University, and there I have also such an huge calculation in, and you can also look in this calculation, in this example, that is in English, that is in the after English, it is also in Russian, and you can read this additional example, especially in preparing to the examination in the end of the course. Yes, what have we to do? At first, we have to calculate the uncorrected transfer function. That is m and n. And the formulas are, again, really simple. N is delta y uncorrected divided by delta x. Y uncorrected means that you calculate the mean of each line. Then have you separated the random and the systematic error. Y uncorrected is the mean. Y uncorrected is the mean, delta y uncorrected divided by delta x. And then you can calculate with this formula the n, y uncorrected minus mx. And you can calculate it when you have the line between y uncorrected from the first two lines between 10 and 20 centimeter, you can calculate the n with the upper point and also with the lower point, because the line is crossing 2 points. Both points will be crossed by the line. You calculate with the same n, and therefore you can calculate with both the points. And then you calculate the kn, 1 divided by m, and kn is minus n, so that you have also the calibration constants. And the easiest way is every time when you make this table, important is that you write your transfer function, that is this one, and your calibration function between the points, that you write it between the points. You have every time one function less, one lines less than points, because the linear approximation lines are every time between the points. And here you calculate y uncorrected. That is a mean from the first measurement row. The first measurement row, the mean is 1.425. That is the mean from the second measurement row, 10 centimeter and 20 centimeter. And you calculate here the m with delta y uncorrected, this delta divided by this delta. This delta is every time 10, but here you have to calculate the delta y uncorrected. And then you get these values for m. You calculate n. N is y uncorrected minus mx, and you can calculate it with this point, but you can also calculate n with this point. That leads to the same n. You use the same m, and this line is crossing this point, and therefore you get for the n the same value when you calculate in this point and when you calculate in this point. And then Km is 1 divided by m, and Kn is minus n. So, and that you do for every point, so that you have here the transfer function, and here you have the correction function with linear approximation step by step. And then can you put it again in your software? You ask less than 1.74. You see less than 1.74, then you have to correct with the first correction function. Less than 1.9, you have to correct with this. Less than 2.027, you have to correct this with this. But in the end, you ask not less than 2.1, you ask bigger than 2.027, then correct with the last line, and bigger than 2.027 include also values which are bigger than 2.168. 2.168 is, let me show it here, 2.168 is the mean over this scattering values at 50 centimeter. And you see this value is already bigger than the mean. And this is for the calculation then also included. The 2.29 is bigger than 2.168. But when you ask the last line calculate with bigger than 2.027, then included this also values which are bigger than 2.168 with the same function. Of course, you get then a value which is bigger than 50 centimeter, but you know then you are out of the range, and the errors which are given, that is all not valid anymore because you are out of the range, but the device is working. So, and when we draw all the functions, then have you here the uncorrected function. That is a function of the system. X is the input value between 10 and 50 centimeter, and Y uncorrected is the output value. Now we have the correction function. There is the Y uncorrected, the input value, and Y is the output value, but when everything is right calculated, is Y equal to X, because that is the aim. And here we have the corrected function. That means overall, X is on the input side, Y is on the output side, and the aim is Y is X. To understand these three functions, it is again good to look in these overview pictures here. You see the uncorrected function, the transfer function, that is a function of the system. X is going in, Y uncorrected is going out. Y uncorrected is a ADC number or a voltage number, any kind of number. Then the correction function. The correction function is Y uncorrected is going in, and Y is going out under the condition that this Y is equal to X. And the corrected function is the function over everything, and that is every time Y is x. That's every time y is x. And when we look for the functions, you see here, when you have this uncorrected function, then is the correction function the mirror function. It is mirrored on the line y is x. That means the correction function is a mirror function of the uncorrected function. And the uncorrected function is going this way, then has a mirror function going this way. Every time exactly opposite. And the mirror is y is x. And when you switch behind a function and the own mirror function, then get you every time y is x. That's the mathematical background. So, and at last, we have now to calculate the random errors in two ways. At first, we have to calculate it back. What would be the corrected value for the single values at each point? You see, oh, sorry, wrong direction. You see here, that are the voltages, what you read into your computer and what you correct. And you use now the same program, the same correction, that you correct the mean of these voltages to the 10 centimeter. But the single value can be different from the mean. And a value which is bigger than the mean, you get also a value for the centimeter, which is bigger than the 10 centimeter. And I have calculated this here, and you see the corrected values are scattering around 10 centimeter, but the mean should be 10 centimeter because you have corrected the mean from the uncorrected value to 10 centimeters. Therefore, the mean should be 10 centimeter. And that's the same in all the other points, in all the other lines, that you have a scattering about the true value, but the mean should be the true value. And then can you calculate the standard deviation of each line? But normally you find the standard deviation, the biggest standard deviation in the last line, because the standard deviation is an absolute value in centimeter. And in this case, you find the biggest standard deviation at 50 centimeter. It's 4.84 centimeter. You see, it would be a terrible measurement device with such a huge error, but for the demonstration, it is good when we have also a little bit bigger errors. The single standard deviation is 4.84. That means that 68% of the measurement values are in the range 50 centimeter plus minus 4.84 centimeter. And when you need it a little bit more with a higher security, you say, where are 95% of my measurement values? Then you have to double the standard deviation, 50 centimeter plus minus 9.6 roundabout centimeter. In this range, then are 95% of the values. And for the second kind of the expression of the random error, you calculate, you look for the biggest deviation from a true value. In this case, we have it here, but you can find the biggest deviation from a true value everywhere, because this the error class is a relatively error in percent. Therefore, you can also have the biggest deviation in one of the lower lines. But in this case, it is N8. That means you have measured 58 centimeter, 58.65. That means 17.3%. And then you define an error class, and you can say 20, you can say 25, you can say 18. There is no rule, and therefore this is not a scientific method, but it is used in the industry very often. But you see, it's a terrible big error. Our demonstration measurement device has so big errors because we would like to demonstrate the errors, but you can also have the biggest error in another measurement device at 1.3%, and then you say the error class is 1.5%, but the system is exactly the same. Have you questions? Okay, if not, then I wish you a pleasant day, and I hope you enjoy the weather and look a little bit in the city, and yeah, have a pleasant day. Bye-bye.
Thanks, bye.
Thanks.
Thanks, bye.